All right, so for today we're doing Chapter 9, Section 6, Vectors in Space. So we're adding our third dimension. So if we take a different perspective on our XY axis and look at it from above, and then we add in a Z axis that goes, I guess this is more north-south. Our y-axis goes this way, and our x-axis goes this way. This is our rectangular coordinates in space, adding that z dimension. We call it the right-hand rule. So if you take your right hand and give it a thumbs up, hey, and your thumb is going to be the z. Your fingertips are going to be the X, so you're going to point in the X direction, and your wrist is going to go in the Y direction. So as you are drawing these on your paper, you want to use your right-hand rule to help you put that together. When x is equal to 0, what results is the z-y plane. When y is equal to 0, the xz plane results. And when z is equal to 0, the yz plane results. This bottom guy right here. When you have z equals 3, you find 3 on your z axis, and all the points that spread out at that z level, all the x and the y values, are the plane z equals to 3. Same thing with 4, y equals 4. So you go to your y axis, find 1, 2, 3, 4. All the points spreading out on that y equals 4 plane is, so whereas before we had x equals 3 was a line, now in 3 dimensions we have just one value equaling a number that is a plane. All right, I love the distance formula for 3-dimensional because it's the same as 2-dimensional, so there's no extra work required except we have the third coordinate. So same distance formula, the difference between the x's squared, the difference between the y squared, the difference between the z squared. Add all those together, square them, add them together, and then take the square root. So the distance formula is the same process, which I love. All right, so let's see how that works with real points. If I have point 2, -1, 4, and those a 3-dimensional point goes x, y, and z. X's go first, y second, just like normal coordinate, and then the z is always the third guy. So we are going to go 2 minus, or -3 minus 2 squared, 5 minus -1 squared, -1 minus 4 squared, add all the, square them, add them all together, and then take the square root. It looks like this. So here we'll get -5 squared, 5 plus 1 is 6 squared, and -1 minus 4 is -5 squared. We go ahead and square those according to our order of operations. Thank you, pre-algebra. 25 plus 36 plus 25 is 86. And the square root of 86 does not simplify. So the distance between these 2 points is the square root of 86, which is close to 9. All right, let's add the vector layer to our 3 dimensions. So we had, for a 2-dimensional vector, we had an I, we had a J, and if we follow the pattern, what is our 3rd dimension going to be? K. Okay. So our 3-dimensional vector is going to be AI plus BJ plus CK. And because when I'm writing vectors by hand, it's very difficult with a pencil to efficiently get a bold letter. When I write my I vector, I write an I, and then I put a vector arrow on top of it. When I write J, instead of a dot, I write the J, instead of a dot, I put a vector arrow on top. Now same with the K, lowercase k with a vector arrow on top. All right, if V is a vector with its starting point at x1, y1, z1, not necessarily on the origin, and a terminal point at x2, y2, z2. If V is the vector from P1 to P2, then V is equal to the position vector. Okay, so there's a little rule with vectors. It's easier to fuss with vectors when they start at the origin. So if you have a vector that does not begin at the origin, we usually will find its position vector and go ahead and move it back to the origin. So the position vector is going to be x2 minus x1i plus y2 minus y1j plus z2 minus z1k. So if I move this vector so that its P1 is now on the origin, I rewrite it as its x-coordinate, the difference between its x-coordinates I plus the difference between the y-coordinates j plus the difference between the z-coordinates k. All right, so if we want to find the position vector v, if we have a vector that goes from 2, -1, 4 to 1, 4, 2, we are going to go ahead and subtract the x-coordinates, 1 minus 2, subtract the y-coordinates, 4 minus -1, and then subtract the z-coordinates, 2 minus 4. When we do that, we get -I, 4 plus 1 is 5j, and 2 minus 4 is minus 2k. So this is the position vector that for points P1 and P2. Because it's easier to fuss with vectors that start at the origin than with vectors that are roaming around in space. All right, we're going to do some stuff with vectors. It's going to be great. So everything is the same except we have now a C coefficient that goes with our K part of our vector. So when we add vectors, we're still adding the coefficients of each of the components. When we're subtracting those components. And multiplying by a scalar, we're still multiplying each of our coefficients by that same scalar. And then the magnitude is equal to each of the coefficients for the components squared added together. All right, so let's do some operations on some vectors. If I have V equals 3i plus 5j minus 2k, and W is equal to -2i minus 2j plus k. If I want to add those two vectors together, I just go ahead and add the I coefficients together to get my new I, my j coefficients to get my new j, and my k coefficients to get my new k. So 3 minus 2 is 1i, 5 minus 2 is 3j, and -2 plus 1 is -1k. If I'm going to subtract the vectors, I'm going to take my v vector and I'm going to take the opposite of each of my w components for my w vector. So it's going to be 3 minus negative 2, which is plus 2. It's going to be 5 minus negative 2, which is 5 plus 2. And negative 2 minus 1. So we get 5i plus 7j minus 3k. With a k. All right, so we can multiply by a scalar. So 3v, it's going to take all those coefficients and multiply them by 3. So we get 9i plus 15j minus 6k. And we can combine those two operations together. We can multiply by a scalar and then subtract it. So I'm going to multiply each of my coefficients by 2 and each of these coefficients by 3, and then I'm going to subtract the two vectors. So I get 2 times 3i is 6i, 2 times 5 is 10j, 2 times negative 2 is negative 4k. I'm going to subtract it from 3 times negative 2 is negative 6, 3 times negative 2 is negative 6, and 3 times k is 3. 6 plus 6 is 12, 10 plus 6 is 16, and negative 4 minus 3 is negative 7. For C, we're just going to find the magnitude of V, and remember that's taking each of these coefficients, squaring them, adding them together, and taking the square root. So it's 3 squared plus 5 squared plus negative 2 squared, 9 plus 25 plus 4. When I add those together, I get 38, and the square root of 38 does not simplify down other than 38. If I want to find a unit vector, crazy enough, we call the unit vector U for unit. It's one of those that actually makes sense. Our unit vector is our regular vector divided by the magnitude of our vector. What it does is it takes whatever length our vector is, keeps the same direction, but shrinks it down to 1 unit, creating a unit vector. So it's our regular vector divided by our magnitude. And remember, the magnitude is only a number, just a symbol. So when we want to find a unit vector, real quick before I move on, our unit vector is equal to V divided by the magnitude. So if I'm just looking at my vector, I can rewrite this as the vector is equal to the magnitude of the vector times the unit vector. There's just a different way to write the same formula. Okay, find a unit vector in the same direction as this V vector. V equals negative 2i plus 4j plus 3k. So we are going to definitely find the magnitude. So we're going to square each of those coefficients, add them together to get 29, and the magnitude of V is a square root of 29. Now, if you notice, when we can't simplify a radical, we just leave it in radical form. The unit vector is our regular vector divided by the magnitude we just found. And since it is not allowed to have a radical on the denominator, we rationalize the denominator by multiplying the top and the bottom by square root of 29. So that's how we get negative 2 root 29 over 29 I, 4 root 29 over 29j, plus 3 root 29 over 29k. All right, so now we're bringing in what we did in the last section. We're finding the dot product when we have a three-dimensional vector. So the dot product is the same as it was before. With a two-dimensional, we take the coefficients for our I component and multiply them, and add that to the coefficients of the j after we multiply them. But since we are three-dimensional, we're going to add on the product of the coefficients for the k part of our vectors. So the dot product changes, it adds this little c1 times c2. Let's apply this dot product to these two vectors. V equals 2i plus 4j minus 3k, and w equals 3i minus j plus 5k. We are going to do 6 different things. We're going to find the dot product of v and w, find the dot product of w and v, find the dot product of v with itself, w with itself, and the magnitude of each vector. So the dot product between v and w, we get 2 times 3 plus 4 times negative 1 minus 3 times 5, which is 6 minus 5 minus 15. 6 minus 5 minus 15. Sorry, 6 minus 4 minus 15 is negative 13. We switch those around, so each of these items switches. We still get 6 minus 4 minus 15. So the order doesn't matter for dot product. For v, the dot product of v with itself, we get 4 plus 16 plus 9, which when we add those together is 29. And then the dot product of w is 3 squared plus negative 1 squared plus 5 squared. It's 9 plus 1 plus 25, which is 10 plus 25, or 35. The magnitude of v is the square root of 29. We found that in the previous problem. And the magnitude of w, I'm going to guess it's the square root of 35. Oh, that's right. Because remember, the relationship between the dot product of a vector in itself is equal to its magnitude squared, just like in our previous section. All right, so property of the dot product are what we already discussed. U dot v is equal to v dot u. We can use the distributive property, so we can go, if I have 3 vectors, u, v, and w, I can add the 2 vectors together and then dot product with the u, or I can dot product u and v and add it to the result of the dot product of u and w. A vector dot itself is equal to its magnitude squared, and the 0 vector times a vector is always equal to 0. So 0 vector dot times dot product with the vector. All right, we're going to find the angle between 2 vectors. Yay! If you recall, we have this formula, cosine theta equals the dot product between u and v divided by the product of the magnitudes. This was same as before, and we're going to use this to find the angle between the 2 vectors. Okay, so we want angle theta between u equal negative 2i, negative 2j plus k, and v equal 3i plus 5j minus 2k. So we're going to find the dot product, which is negative 2 times 3 minus 2 times 5 plus 1 times negative 2. That's negative 6 minus 10 is negative 16. Minus 2 more is negative 18. We're going to find the magnitudes of each of our vectors. So for u, it's going to be 2 squared plus, which is 4, plus 2 squared, which is 8 plus 1, which is 9. Square root of 9 is 3. For v, it's going to be 3 squared plus 5 squared. That's 9 plus 25. It's 34. Plus 4 more is 38. So that's a square root of 38, and we can't simplify that down anymore. And then now let's put it together into our formula. Cosine theta equals the dot product of u and v divided by the product of our magnitudes. So that's negative 18 divided by 3 times root 38. If we write the approximation, which we can write it, but I would not recommend using the rounded value when you're finding theta, we get negative 0.9733. So when you're putting this in your calculator, just keep this here. So I would have inverse cosine, parenthesis, negative 18, open parenthesis, negative 18 divided by open parenthesis, 3 times root 38, close parenthesis, and then apply it. We get theta equals 166.7 degrees. All right, direction angles of a vector. So we have a vector. We want to know these 3 angles. Alpha is the angle between V and I, or V and I is the positive x-axis. So alpha is the angle between your x-axis and your vector. Beta is the angle between V and J, or the y-axis. So here's beta right here. And gamma is the angle between V and K, or the positive z-axis. So between your vector and here is gamma. So to find those angles, we are going to use these formulas. The cosine of alpha is our A coefficient, so it's a coefficient of I, divided by the magnitude of our vector. Cosine of beta is the coefficient for our J component, divided by the magnitude. And the cosine of gamma is the coefficient for our K component divided by our magnitude. The numbers cosine alpha, cosine beta, and cosine gamma are called the direction cosines of the vector V. Direction cosines. So if we wanted to find the direction angles for 2i minus 4j plus 5k, you're definitely going to need the magnitude first. So we find the magnitude taking each component of each coefficient, squaring it, adding it together, taking the square root. We get square root of 45 equals 3 root 5. So to find the direction angles, we're going to take each of its components. 2 divided by 3 root 5 is equal to cosine alpha. Take the inverse cosine of that. For beta, we get negative 4 divided by 3 root 5, inverse cosine. For gamma, we go 5 divided by 3 root 5, inverse cosine of that. All right, so a property of direction angles is similar to our identity for trigs, but a little bit different because there's no sign. So cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. All right, the vector V makes an angle alpha equal to pi over 4 with the positive x-axis, and an angle beta equal to pi over 4 as well with the positive y-axis. An acute angle gamma and an acute angle gamma with a positive z-axis. Find gamma. We're going to use that cosine property. Cosine squared of pi over 4 plus cosine squared of pi over 4 equals cosine squared of gamma equals 1. Cosine of pi over 4 is root 2 over 2. I'm going to go ahead and square that, and we get 2 over 4, which is 1/2. 1/2 plus 1/2 is 1, plus cosine gamma squared equals 1. I subtract 1 from both sides, and I get cosine squared gamma equals 0. Take the square root of both sides, I get cosine gamma equals plus or minus 0. Oh, same, just a 0. And we know that because it's an acute angle, gamma has to be 0. Show that any non-zero vector v in space can be written in terms of its magnitude and direction cosines. So any vector can be written as the magnitude of v times cosine alpha I plus cosine beta j plus cosine gamma k. In terms of its magnitude and direction cosines. Okay, so we're going to let vector v be ai plus bj plus ck. And from each of the equations, it's the one cosine alpha equals a over v. The one from before, cosine. We get a equals the magnitude of v times a cosine alpha. B equals the magnitude of v times a cosine of beta. And c equals the magnitude of v times a cosine of gamma. All right, so we're going to go ahead and replace each of these coefficients with the magnitude times the cosine of the angles alpha, beta, and gamma. Once we do that, we're going to go ahead and factor out the magnitude, which leaves us with our vector v equaling the magnitude times cosine alpha I plus cosine beta j plus cosine gamma k. And that's all. Before I conclude this section, I do want to say, look at the example problems in your textbook. We have just gone over formulas and the very basics. How they work in application problems there's a different flow and process. So make sure before you do the practice assignment, before you take the assessment, you look at each of the practice problems and use those as your reference for completing your assignment.